Hi, folks. Here's another helpful hint. Problem number 12. So this is chapter 11, problem set number 1. I like this problem. It's got everything in it. It's got energy, rolling without slipping, centrifugal force, centrifugal acceleration, all that good stuff. All right, so we have a solid brass ball. Get my inking tool ready to go. And here's the interesting feature about this problem. They say that the radius of the ball is really small, really, really small compared to the radius of the loop. So that's helpful. So you don't have to overthink that one. I hope that makes sense. So it says, what is h? Okay, the height where we release this ball, such that it's on the verge of leaving the track when it reaches the top of the loop. So when that ball reaches this point right here, the normal force pretty gosh darn equal to 0. So here's the concept. The sum of the forces when that ball's at the top of the loop. Okay, I'm going to indicate the following. Okay, and it's a radial line of action in this case because there's centripetal force. We have the normal force down, which is 0. I'm just going to stick it in the summation. We have the weight down, and the direction of the centripetal acceleration is down. That's equal to m, in this case, v squared over r. And you'll recognize the special relationship where the minimum speed that the ball has to have in order to remain barely in contact with the surface is related to rg. Where in this case, r is not the little r of the brass ball, but it's equal to the radius of that loop. Okay, so we're gonna go with that. All right, how do we set this thing up? Well, we're going to use energy to start this problem off. So state 1 will be the energy of the ball when it's here. It's starting at height h. Let's call that state 1. And then state 2 will be the energy that the ball has rolling without slipping when it reaches the top of that loop. Okay? All right. Let's sketch it out. This is a helpful hint. So I'm going to remind you folks to solve the rest of it, but this is to get you guys going. All right, so at state 1, we've got gravitational potential, okay, just sitting there. It's going to release it. And then at state 2, it's going to have gravitational potential energy again, okay, because it's starting here, but it's going to end up still above the ground relative to where it started. And then because it's rolling without slipping, there's the kinetic energy associated with the rotation of that sphere and the kinetic energy associated with the translation of that sphere. Okay, so let's see how far we got with that one. We have mgh is equal to mg. Now, notice that where we are in terms of the final height at state 2, that's going to be 2r. I hope you see that. Okay, so it's going to be 2r. So that's the diameter of the circle of that, that thing, that loop-to-loop. Okay, so once the rolling without slipping object reaches the top of that loop, it's got 1/2, in terms of the energy, 1/2 I omega squared, plus the translational 1/2 mv squared. All right, now that's the relationship. Here's some magic substitutions. Know that omega is related to v over r, okay? And know that that's the radius of the brass ball. So stuff's going to cancel. Solid brass ball, what's the rotational inertia? And I forgot to specify it in the other two problems, so I apologize. The rotational inertia for a solid spherical object is 2/5 m r squared. Okay? All right. I think you can do the rest. So this is part A. So what is that height such that it's barely in contact? Well, I'll give you the answer so you can compare. The height's approximately 37 centimeters or 0.378 meters. Okay, so that's That's where it's going to be released, such that it's barely in contact with the loop. Okay, that's part A. Part B. Okay, part B. Magnitude and direction of the horizontal force when it's at Q. All right, now same deal. Uh, Instead of state 2 being at the top of the loop, specify state 2 at Q. Okay, so this is for part B. So we have a new state 2. Okay, so at Q, one of the states of energy. Now, notice what the potential energy is at state 2. It's mgr this time. Okay, and you're going to come up with a velocity, okay, a speed, and again, you're going to specify the energies at state 2. And this time, when you substitute omega equals v over r, you're going to solve that whole expression for v. So I'm going to assume that you're going to, specify the state conditions of the energy at state 1 and the energy at state 2. Okay? You can borrow the idea from here. Just know that what you're substituting is in relationship to where the object is at Q. But here's the velocity you should get, so you can check your work. You should get 3.13 meters per second. Okay, give yourself a high five if you get that after it's all said and done. And then you're going to apply Newton's laws of motion once again for uniform circular motion. I guess this is for part B. Sum of the forces when we get to Q is equal to ma sub c. All right, and the force, let's call it that normal force when it's at Q. Expect to get an answer around 1.96 times 10 to the negative 2 newtons. All right. So there's your, I hope, a helpful hint. So notice that we had applied energy, state 1, state 2. The rotational inertia of a solid sphere, 2/5 mr squared. Okay, so things are going to cancel, like the mass. There's a mass in each term. In terms of the rotational inertia, you get an r squared. But then when you substitute v over r for omega squared, okay, the r's are going to cancel. So things simplify. So just be patient when you come up with your expressions and then make your substitutions. Notice that we have grams, not kilograms, and we have centimeters, not meters. So express everything in meters and kilograms. So there's your helpful hint for problem number 12.